Hello students, I'm Dr. Tanmoy Biswas. I welcome you all in my channel Chemistry, the Mystery of Molecules. Today's topic of discussion is one MCQ in front of you about dihydrofuran derivative. So the question is in front of you. I request you student, please pause the video, read the problem carefully, try by yourself, and whatever answer you get, please write in the comment box along with few words explaining your answer, because remember, self-evaluation is essential for improvement, and that's why you should try. And don't worry, after some time you will get the right answer with explanation. So I believe you have tried by yourself. So let's start. In this problem, before going to details, just look at what condition given: aldehyde and with tritanium tetrachloride, means Lewis acid. So it's actually a electrophilic reaction condition, and second is very strong base. And if you look at this molecule, this is little unique. What is this unique? Because one side is silicon attached to direct carbon, means this alkene silicon, silane, and another side is silyl enol ether. So one side of the molecule is electrophilic, another side it must be nucleophilic, obviously. So which center is more nucleophilic, this carbon or this carbon, and why? So let's understand this thing first. So this nucleophilicity arises because of this oxygen lone pair delocalization, means it can come here and it can open. So ultimately it will produce, this is a carbon ion, and this oxygen is having a positive charge, this much. Now the nucleophilicity will be reflected because of this carbon ion part. Okay, and this is actually a nucleophilic, but more specifically if I say this is actually mild nucleophilic. Why? Because the negative charge or electron density is coming at this position because of resonance, and that is associated with charge separation, and this charge separation is also associated with some unstabilization. So that's why the contribution of this canonical form to the overall electronic distribution in this neutral molecule will be less. So that's why it is a mild or weaker nucleophile. So consequently the electrophilic part need to be strong, and that actually happens. How? This titanium 4 plus from TiCl4 reacts with aldehyde and form these adapt, you can see here, and after donation, means electron donation to titanium 4 plus, these molecule became more electron deficient, this aldehyde carbon. How? Because it can come here and it will produce, this is O minus, and these O minus got relatively more stabilized because coordination with titanium, and this carbon is carrying positive charge, means after the coordination with titanium 4 plus, this carbon atom of aldehyde, means aldehyde carbon, became more electrophilic. So consequently what will happen? These lone pair will pushed here and this part will attack here, and this is actually double bond, so it will open. So after workup, what it will produce? In the first step, what you can expect? The first step is actually just I am showing the main part. So this is OSI-Me3. Fine. Sorry, let me draw it very carefully. This is Si-Me3. Okay, oxygen is carrying a positive charge, and this aldehyde produces this alcohol. So this is another silicon, means this Si-Me3. Okay, now this is actually a protonated carbonyl compound or type silicon attached. This oxygen is carrying a positive charge. So in the next step, during the hydrolysis, these will be hydrolyzed and ultimately it will be converted into corresponding ketone, and initially there will be O minus, it will be converted into OH. So this is the thing. You may consider alpha beta. So beta hydroxycarbonyl derivative. Now this is the product of the first stage. In the next stage, what you can expect? And by the way, you will think that, sir, this looks like Mukayyama aldol condensation. Yes, it's true, but why Si-Me3 group is there? Remember student, Mukayyama reaction is the reaction of this enol ether. That enol ether part is hydrolyzed and this is converted into carbonyl, but this was other silicon and this silicon was neutral, directly attached to carbon, so it will not go. Okay, and the next step, this is lithium HMDS. If you look at the structure of this lithium HMDS, actually this is a very big base. Big base means this is the N minus and this is the lithium plus. Okay, and because of these two bulkier trimethylsilyl group, it cannot act as nucleophile. It has a very strong base. I've already used, I know it's a very reactive molecule. So it will instantly abstract the proton from this oxygen. So this bond will be deprotonated and O minus Li plus, fine. Now remember student, recall the Peterson olefination in presence of in basic medium. So what will happen? This oxygen will attack this silicon center. We know that silicon has energetically accessible vacant d orbital, so it can accept excess electron density because this silicon is student octet field, H electron field, but still it can take because of this. And second, this oxygen silicon bond is significantly more stable due to d pi p pi back bonding, means the lone pair of oxygen could be delocalized into the silicon's vacant d orbital. So that's why this bond is stable. So first it will prepare this 4-member ring. Now second, silicon have one negative charge, means excess of electrons. So what it can do? So these electron could be given here and it can open. So ultimately this part will be alkene. So Peterson olefination just sometime before he told. So this part will be alkene and other side is the silicon trimethyl O minus, or later on after workup it will be OH. So stable silicon oxygen bond is produced. So in this way, this is alpha beta unsaturated carbonyl could be produced after this reaction. Sorry. So what are the key steps and reaction name reaction associated with? First step is Mukayama aldol addition reaction and the chemistry of enolate. I have already discussed this enolate many videos. Second is acid base reaction between this lithium HMDS and OH. Third step is Peterson olefination to get the alkene, and finally this Wittig type elimination, means obviously this included in between the belongs to the Peterson olefination reaction, ultimately produces alpha beta unsaturated carbonyl. So alpha beta unsaturated carbonyl derivative. So what is the answer? Answer is alpha beta unsaturated carbonyl, simple, option C. Now so this is the answer. Now why not others? First of all, this double bond how came? Not possible. No oxidant I have given, just it's a base, not possible. Aromaticity, not possible, not possible. So simple. Now if this question appear in your exam less than 30 seconds, how could you solve? First of all, you need to understand which center is more nucleophilic. Obviously this because of this resonance, means enol ethers nucleophilicity, and the condition is Mukayama aldol reaction. Point number 1. If you understand this thing, so point number 1, one beta hydroxy carbonyl derivative will be produced in one, and second simple base. So this part will be same, but this part will no aromaticity because no oxidant I have given. So option A gone, option B gone, obviously option D also gone. So this part will remain. What is left? Option C. So this is very easy using following these tricks, but I always request you student, please don't follow tricks at the beginning, just learn the chemistry properly, later on you follow the tricks, then you will get success very easily. So in conclusion, what you have learned today, that enolates are moderately nucleophilic. To utilize their nucleophilicity, the other carbonyl compound needed to be activated or more electrophilic. Point number 1, titanium 4+ is a very strong Lewis acid. It activates the aldehyde such that nucleophilic attack by the enolate became possible. Silicon is slightly less electronegative compared to carbon. So this carbon silicon bond, if you look, this carbon has delta negative character, fine, but this SiOMe3 group shows both -I and +R effect, and in this case +R dominates, okay, due to the lone pair of oxygen which donates and ultimately activates the carbon-carbon double bond. Now lithium HMDS is actually a non-nucleophilic base, or you can say it's a bulky base. It selectively abstracts the acidic proton or OH. And finally, alkoxide can act as nucleophile for the silicon center, as silicon oxygen bond is significantly stronger due to d pi p pi, actually d pi from silicon and p pi from oxygen back bonding. Okay, so this is the end of this discussion. I believe this video may be useful. If it is, please help this channel to grow, and if possible, please visit my another channel, Climate and Chemistry. Thanks for watching. See you in my next video. Bye bye.